Okay, did you remember what we talked about Friday? So Friday's lecture was really important because it kind of laid the foundation for series. Super important ideas. The divergence theorem is probably it's like this key starting idea for talking about any series because it's really focusing on the idea of the series being the sum of the list of terms in an infinite list, a sequence, right? So what was the general idea of the divergence theorem? General idea. Remember this.
If a sequence is divergent or converges to anything but zero, then the series is divergent.
That's right. And does that make sense? So why does it make sense that if a sequence converges to something other than zero, so if why does it make sense that if this is what needs to make sense to you, not something you memorize? Why does it make sense that if a sequence converges to something other than zero, that series has to diverge? Tell the person next to you. Why does it make sense that if a sequence converges to something other than zero, the series has to diverge? It needs to make sense to you, not something you memorize. Go. Okay, volunteer. Why does it make sense? This is on the exam. This question is on the exam. You have to show us that you understand why this is true. Okay? The sequence converges to something other than zero, therefore the series diverges. Why? Yes, sir. Right. When n gets large, you essentially in your list you have that same value over and over again in your list in your sequence. If n gets very big and you're approaching a certain value, then essentially it's like you have that same value over and over again in the list. So what's going to happen if you add them up? You're just going to keep adding the same non-zero value over and over again, which could never converge to a single value. That will just keep getting bigger, positive or negative, if your limit of the sequence is negative. Okay, again, that needs to make sense. That needs to make sense. Okay, the harmonic series, the harmonic series is the sum of the sequence 1 over n, and the limit of that is 0. So that's easy. So therefore the series converges because the limit is 0, right? No, what did we find on Friday? So what does this have to do with the divergence theorem? So this first of all, so it doesn't meet the necessary condition for the convergence theorem. We have a sequence that does go to 0. So the point of this is to say, just because the sequence goes to 0, then now your series might converge, but there's no guarantee. It depends on the sequence. This particular sequence still we've showed that it could just add up. It adds up and just keeps getting larger and larger. So in order for a series to converge, the necessary condition is that the sequence has a limit of 0, but that's not sufficient. It's not enough. We'll talk more about that today. Okay, and so we said we found another series that diverged, and all of the terms were what? Less than or equal to, or greater than or equal to the 1 over n. Do you remember? We found another series such that all the terms in this series was either less than or equal to or greater than or equal to, and that allowed us to claim that this series diverged. What was it? This was the one we compared it to. Was that series less than or greater than 1 over n? Less than. And it diverged. We have a series that's less than the one we're interested in, and it diverges. Therefore, what about ours? The one we're interested in. Has to diverge, because it's big. It's bigger than one that's already going to add up to infinity, right? Or add up to, infinitely large. So how could a comparison test show convergence? How could a comparison test show convergence? What would we need? So we've got our. So let's do this. So here's the formal. Here's what we used to show that the harmonic series was divergent. It says, there shouldn't be a comma there. Let a series AN and a series of a sequence BN be series with all positive terms. If BN is divergent and AN is greater than BN for all n, then AN is divergent. That's exactly what we use. That's a kind of a generalized version of what we use to show that the harmonic series is divergent. In that definition, which one is the harmonic series? AN, sum of AN, or sum of BN? We did an example, the harmonic series. In our example, would the harmonic series be the sum AN or the sum BN? AN, right? And our alternative was BN, and ours was greater than our alternative series for all the terms, and we knew it was divergent, so then therefore the harmonic series is divergent. So I want you to rewrite this for comparison that would show that a series is convergent. Can you rewrite it yourself? How would you be showing that a series is convergent using the same idea of comparison? See if you can write it out, and then I'll take away the box and you see how you did. So how would you rewrite the alternate version of this to show that a series is convergent? Go. So actually write it down in your notes as if you were copying it down off the screen, and then we'll see if you got it right, okay? So actually, pretend that you're copying it down off the screen to have it in your notes, and then you'll see if you have it right or not. Okay, you ready? Here's what it is. Should be. Come in. Here we go. let the two series have all positive terms. If the sum Bn is convergent and An is less than or equal to Bn for all n, then An is convergent. How many people got it before I put it up? Okay, a good number of you. So if you're going to show convergence, then you have to have a comparative series that converges, and yours has to be less than that one, right? The one that you have has to be less than your comparative one. For all the individual terms have to be less. Therefore, the sum would also converge. It's like you're squeezing it between this other one that you know converges and 0. So you have another series you know converges, and then yours is like ends up gets squeezed between the other one that has a convergent sum and 0. So yours must be convergent as well. Does it make sense? It should make sense. So what if you have a convergent series? So you're testing a certain series, and there's another one that's convergent, and the terms of yours are all greater than or equal to the one that you know is convergent. What's the conclusion? So we know that this one converges. This is like our Bn, okay? And then our An is greater than or equal to Bn for all terms. And the series Bn converges. What about the series An? Converges or diverges? What's that? Diverge. So if yours is greater than a convergent series, you should be thinking no conclusion. No conclusion. It might converge, it might diverge. Okay, so you have a convergent series. There may be series whose terms are all greater than that also converge. Certainly there are series whose terms are all greater than that diverge. So that would be there'd be no conclusion to that. Okay? So if you have a series that converges and the series you're testing is greater than that for all terms, that may or may not converge. There's no conclusion to that. So to prove divergence, you have to have a comparative divergent sequence such that the one you're doing is always greater than it. Then you can say divergent. Convergent, other way around. You have to have a comparative sequence that gives you a series that's convergent, and then the one you're looking at is all the terms are less than or equal to. And it gets squeezed in between that one and 0. Okay, back to our last question. What about the general form of a geometric series, and when does it converge and to what value? So I went through that fast, kind of at the end of class for time's sake, so I'm not going to go through it again. You've got the video. You can just pause it and pretend that I took 5 more minutes. So you have time to listen to what I say and pause it and think about it. But the form of a geometric series is? Some more room here. So the form of a geometric series is a r to the n minus 1. And so you should be able to write out the terms of that. So let's practice. When you see that, you think what? You see that, think what? Practice. Don't look at your notes. Pretend you... Remember? When you see this, your mind thinks what? Write it down. When you see this, your mind thinks what? Write it down. Write it down. That means you have a pencil in your hand and you're writing it down. This is not the movies. Somebody new, tell me what your mind should think when you see that. Did you get it? No, that's not what you know. That's not what you think. What do you think when you see that? Yes, sir. A, AR. Oh, but I'm adding those, okay. So tell me again. That's what that means. That's the meaning of that notation right there. It means let n equals 1, get the term. Let n equals 2, you're going to add that on. Then let n equals 3, you're going to add that on. Okay, so let's look at this and let's think of an alternate way to write this. This is kind of like AR to the what? 0, right? So what would be another way to do this? What if I wanted to say AR to the n instead of n minus 1? Then what would be different? To get the same sum, right? So I want a different way of writing the summation notation to get the same exact sum. Yeah, so we would, instead of starting at 1, we'd start at 0. So here's an alternate way to write the geometric series. It's exactly the same as that, as this up here. Why? Because they both, the key is, they both equal exactly this. That's the key. They both equal the sum of the same terms. So later down the road, we're going to see this. Notice what happened. In the formula, what happened to the n? It got, how did it change?
It just went from n minus 1 to
And so what kind of change is that? From n minus 1 to n? Plus 1, right? N went up 1. And what happened to where we started then to make it be the same? Our starting value went down 1. That's called shifting the index. So if we wanted to shift the index to maintain the same sum, this would be one way to do that. In your formula, n went up 1. So to maintain the same sum, you have to start at n of 1 less. Should make sense. You'd have to start at an n value 1 less. If you're going to increase n by 1 in the formula, that will maintain the same sum. That's called shifting the index. But so now we have two alternatives to the geometric series, and you have to be aware of which one you have. Okay?
So in other words, we can not just shift it just once, we can shift it multiple times.
Right. So what would it be if you started? If you, I don't know why you would want to, but say you wanted to start the sum at n equals 2, but we want to maintain the same sum. So yeah, good. Write that out. So if I want to start at n equals 2, what would the new formula be to maintain the same geometric series? If I started at n equals 2. AR to the n minus 2. Then would give us the exact same terms. It would also be the exact same geometric series. All right, let's do a geometric series example. Oh, so then, yeah, so, and then in terms of now, geometric series is we can actually know when it does converge and when it doesn't converge. So for what values of R did it converge, did we find? from -1 to 1. And this, we said this was similar to our P sequence, right? So P, the sequence converge. A sequence converges if you have P to the n, right? If you have P to the n, that sequence converges for P between -1 and 1. Converges to 0. And we showed mathematically that similarly, the geometric series, which is similar to the series for, it's just really a multiple times that P sequence, just some constant multiple A, times the sum of the terms of that P sequence. That series converges for R between -1 and 1, which for the sequence would have been P between -1 and 1. Okay? So, and then what does it converge to? We found that if R is between -1 and 1, this is what the sum was. This is what you said, which is? Yeah. When R is between -1 or 1, if you were to add up all infinitely many terms of the geometric sequence, you would get A over 1 minus R. And so remember we had the turtle problem, always going halfway to the fence, or halfway across the backyard, or halfway of the remaining distance, always going half the remaining distance. So we got, this was first that he goes halfway across the lawn, and then he goes half of that, and then he goes half of that. He keeps going halfway across, and if he does that forever, we said he would get to the whole way across. If he could do that forever, he would make it. You just keep adding half of the distance to the fence, you would make it. And so then we tested and we said, all right, so we have this, is this a geometric series? What we need is, if we're starting at n equals 1, we need 1/2 to the n minus 1. So I need it to look like that. Start at n equals 1 and have my r to the n minus 1. This is not shifting the index. This is not shifting the index. I want to keep it starting at n equals 1. But I need to make the formula look like 1/2 to the n minus 1. But what do I have? I have really 1/2 to the n. So what? This is 1 less 1/2. And I want to keep it at n number of 1/2s. So what do I need? 1 additional 1/2 multiplied on there. So now I have n 1/2s according to what I started with, right? So that's what I started with. N 1/2s multiplied together. But if I want to make it look like this, I need to show n minus 1 1/2s. That means I need to multiply by 1 more 1/2 to get it to be what we started with. Again, this is not shifting the index. I'm keeping the index starting at 1. I'm trying to get the formula to look like ar to the n minus 1. So if I use that, then what is my a value? 1/2. Also my r value is 1/2. And if so does it converge? Yes, because r is between -1 and 1. And what does it converge to? A over 1 minus r. So the r, we've met the criteria that r has to be between -1 and 1. Therefore, it sums up to 1/2 over 1 minus 1/2. So using our formula for a geometric series, we see we get the same result. We get the same result, 1. So we reasoned it out. We keep adding half of what the distance left to go to the fence, and we can say we can reason out as 1, but then we just kind of show that mathematically by applying a geometric series. Geometric series. Okay, another example of geometric. Questions on that? Anybody have a question? Yeah.
Are there geometric series that add up to other things besides one?
Yeah, of course. This is the only This is the only example we've seen so far. Right? So it's always going to be a over 1 minus r. So if your a and r values are different, you're going to get something different. Yeah. So we'll do one of those. Okay, so here's one. Yeah. All right, I want to actually change this a little bit. I don't know. Okay, let's just go for a hard one right here. Not hard, but it's kind of complicated. It takes a little time here. So the first thing I see is that, how can I see this is going to be geometric? Well, it's because we've got these real number bases, and the power of everything is n, or n minus 1. That's kind of indicating the idea of a geometric series. The next thing I see is that this is really the sum of two fractions. So we have the sum of a sum, and so we can split it up into two sums, right? And kind of analyze them each separately. So I can look at the sum of the first one. So when n equals 1, we're going to get this sum of these two things. And then when n equals 2, we're going to get the sum of these two things. And so since it's a sum of a sum, do you see that we can kind of regroup and we can just take the sum of all those and add it to the sum of all those. Just kind of the changing the order of the sum. Do you see that? So I can really, in your next line, don't erase. So you make a new line. In your next line, you can think of this as and so you should understand that what I wrote previously is equal to this. It's just kind of changing the order of the sum. Rather than going n equals 1 and then n equals 1 plus n equals 1, n equals 2, and n equals 2, n equals 3, and n equals 3. It's just like let's gather up all the n equals 1 to infinity of that first thing. And we'll gather up all the n equals 1 to infinity of the second one, and we'll add them that way. Thank you. Okay, so let's do this. I think the second one, let's do the second one first because it's easier. So how is that a geometric series? Geometric series is a times r to the n minus 1. So can you see what our a value is and what our r value is? What's the a value? It's 1/5. What's the r value? 2 to the n minus 1 over 4 to the n minus 1. 1/2 to the n minus 1. Okay, so my experience is that students' lack of proficiency with the laws of exponents kill them in talking about series, right? So that's basic like algebra. You got to know your laws of exponents, or this unit on series is going to be really difficult. So you should recognize that 2 to a power over 4 to a power is just 1/2 to that power. 1/2 to that power. And then we're going to pull out the 1/5. Okay? So what is this, a convergent or divergent sum? Convergent. And converges to? A over 1 minus r. Equals 2/5. So that second sum is equal to 2/5. Anybody have a question on that? Okay, so the first one, again, I need to make that look like a geometric series. I'm not going to shift the index. I'm going to keep it starting at 1. But I need to make this look like a times r to the n minus 1. So how do I handle that? Do the same thing we did here. I've got negative 3 to the n. What do I need? I really need that to be negative 3 to the n minus 1. Because if I had negative 3 to the n minus 1 over 4 to the n minus 1, I've got my r to the n minus 1, which would be negative 3/4 to the n minus 1. So how can I do that? I just reduced the number of negative 3's multiplied together by 1, and I can't do that. So I need another negative 3. We saw it before. Now that's negative 3 to the n. That's n number of negative 3's multiplied together. Because it's 1 and then n minus 1 more of them, all multiplied together is negative 3 multiplied together n times. So what's my a and what's my r? Find the sum. Go. What's my a? What's my r? Well, first of all, is it convergent? Is it convergent and why? Is that a convergent geometric series? Yes, because r is negative 3/4. It's in that range from negative 1 to 1. Our r value is going to be negative 3/4. That's the r to the n minus 1. Did I do the math right? Okay, therefore this original sum equals what that sum equals plus what that sum equals. And we'll just write it down that way. So how many 35ths is that? 14 35ths? 2 35ths? Did I do the math right? So if you were to add together all infinitely many terms, the sum of all those terms, infinitely many, would be 2 35ths. If we added up the first 50 or first 100, we should have a sum pretty dang close to 2 35ths. Why? Because we know that that sequence, where does the sequence have to go to? What is the sequence? This sequence right here? What's the limit of the sequence? Does it have to be 0? Does the limit of that sequence have to be 0? Talk to the person next to you. Does the limit of that sequence have to be 0? Talk to the person next to you. Or could it be something else? How many people think the limit of that sequence has to be 0? How many people say it doesn't have to be 0? What about the rest of you? Yes, it has to be 0. Remember, because if the limit is not 0 or if the limit diverges, the series must diverge. We've got a convergent series, which requires that the sequence approaches 0. It's not sufficient, but it's necessary. It is absolutely necessary, but it's not sufficient. Okay? All right, so 2 35ths. And what else was I going to talk about? Okay, so what if we broke it up and one of the sums diverged and the other converged? Then what about the sum? One of them diverged and the other converged. Then what about the original sum that we were given? Conclusion. You better be thinking it diverges. Okay? You've got divergent, and then you're going to add more to it, then it's going to diverge. Okay? So in order for, if you're going to have a sum of sums like this, in order for that to converge, every individual sum must converge. If one of them diverges, no chance. Yes, sir? What if both series add up so that that plus that equals 0? You tell me. So then what? Yeah, the series would be 0. I guess so. It could be alternating. I'm trying to think. Is there be a case where this would not be 0, but the sum would add to 0? If it's alternating,
They have the same index.
it has to be 0.
Inside, yeah, it has to be 0.
Okay. Yeah. So if it added to 0, then your sequence would have to be just the 0 sequence. Yeah, it'd have to be the 0 sequence. Your sequence would have to be all zeros. That's the only way that would happen. Alternating? There's not an alternating sequence that would sum to 0?
If you add up the different indices, but then the last one will not be matched.
Okay, anyway. All right. Okay, questions on, so that's questions on geometric series. Is there any questions? Okay.
There's a telescoping series where some terms cancel out, but you can't cancel out all of them.
Because you always have,
Something at the beginning.
right, got it, yeah. Okay, so then there's something called a P series. Is this a geometric series? Is it geometric? Give me one reason why it's not geometric. So what's a reason why it's not geometric? Where is our n? N is the index. So in our formula, n is the base, right? In the geometric series, the n is what? N values are the exponent. A r to the n minus 1. Totally different animal here. This is, n is in the base. Okay, so is it convergent when p equals 1? Is it convergent when p equals 1? Yes or no? What's that? Someone said it. Because? When p equals 1, what series is it? We've seen it before. That's the harmonic series, 1 over n. When p equals 1, we get the harmonic series. And we know that that's divergent. Divergent. So here's the deal. As long as p is anything greater than 1, for p equals 1, it diverges. But let p be 1.01, and it converges. And so you're going to, as we get more and more different kinds of series and tests for convergence, you're going to need to cite to cite your reasons why you're declaring something as convergent or divergent. So, for instance, you would say this is convergent. Or is a convergent, this is better, is a convergent P series since p is greater than 1. So we're going to have different tests for convergence. We're going to know lots of different kinds of series. So you're going to be saying, are series convergent or divergent? And so then you need to give rationale, right? So this is a convergent P series since P is greater than 1. Okay, see this, think what? Write it down. See this, think what? Write it down. What does your mind think when you see that? Write it down. Never want to lose sight of that. What is that? All that scary notation representing? That's got to be what you think when you see it. Somebody new, tell me. Yeah, Joseph.
1 over 1 to the 1.01 power plus 1 over 2 to the 1.01 power. And you just
That's right. Good. This is what you should have wrote. That's what that thing equals. Okay, so let's actually show why. Let's use a different way to show that the harmonic series is divergent, and 1 over n squared is 1 over n squared is 1 over n squared, convergent or divergent? I'll do it in 4 minutes. 1 over series 1 over n squared, convergent or divergent? So this is, I'm not going to write this out all formally, but this is the idea of what's called the integral test. The integral test is a type of comparison test. Rather than comparing one series to another, you compare a series to an integral. So I'm going to look at the function 1 over x. And the series 1 over n. So we know that that's the harmonic series, right? So I want to think about that as each one of those terms as the area of a rectangle with a really big dx, right? So what is I'm going to look at a change in x of 1. No, I want it to be greater than the integral, right? To show divergence. Sorry, we want to use the other side. So here we go. So my delta x is still 1. And remember we learned by improper integrals, what did we learn? We learned that the integral from, say, 1 to infinity of 1 over x. This was that same principle, right? That same principle that if this exponent was greater than 1, this improper integral converged. Do you remember that? And if this was 1 or less, this thing diverged. So is this, what is this? Back right before the first exam. So all this red shaded region here is, remember, 1 over x. It doesn't get to 0 fast enough for that area to be a finite value. It doesn't get there fast enough. Well, this is the same idea with the harmonic series. The sum of the corresponding function, 1 plus a half plus a third, it also doesn't get there by comparison to this integral, because I can take each of these, the area of this first rectangle is 1, right? It's 1 times 1. And what's the area of this right here? 1 times 1/2. So you can think of these as the areas of those rectangles added together. And what about them compared to the area under the curve? What do you see? So that sum total of the blue areas would be the sum total of our series. First rectangle 1, second rectangle area of a half, third rectangle area of 1/3. Base times height. And how does the blue area compare to the red area? And the red area sums up to an infinitely large amount, and ours, the thing we're interested in, is bigger, right? It's bigger. So this is a different kind of comparison. It's a comparison to an integral. So by comparison, of areas. That harmonic series is greater than the improper integral that we learned a month or two ago diverges. Same idea of a divergence. If you have a sum, you know something that's divergence, and your sum you know is bigger than something that diverges, your sum diverges. Okay, I was hoping to show that use the same technique to show that 1 over x squared converges. So we'll start there Wednesday. Okay.